And half a year ago I started to work on locally stationary processes, and I focused my work on cross-validation for such kind of processes. So first I will explain what are locally stationary processes and give some examples. We will see that in some interesting examples there are unknown parameter curves, and we will present a kernel type estimation method for these parameter curves. And in the second part we will focus on an adaptive bandwidth estimation procedure for such kernel type estimates. So first, what are locally stationary processes? Of course, the definition is from the so they were invented in the 1980s, and the definition evolved over time, and today we will take this definition, where we assume that we have IID random variables epsilon t with zero mean, variance 1, and a representation of xt of this kind, which means it's an infinite linear sum of these IID random variables. And these coefficients here can depend on t and n, where n is the length of the time series and t is the observation number. And we have to assume that the coefficients are absolutely bounded by an absolutely summable sequence. And the second part of the definition is that we have a second sequence of coefficients, these functions here, and we have to assume that we can approximate the coefficients of the infinite sum by this other sequence here. Which means that we can make the dependence on t and n more clear on the coefficients. If this assumption is fulfilled, we call a process locally stationary. Of course, n?
N.
You mean
Small n.
Small n is the length of the time series. We assume that we observe xt1, x1n to xnn.
So it can change, so for the structure can change with the number of
Yes.
Mm-hmm.
Of course, there are generalizations of this definition. We don't have to assume that it's linear, but for this work we will assume that we have a linear structure. Important remark is to note that if we fix a time point u from 0 to 1, then we can then this process here is a stationary process. For fixed u, this process is stationary in t, and for fixed u, values t divided by n that are near u, then we know that this coefficient is near this coefficient. And so the idea is that the locally stationary process, which is given by this, can be approximated by this stationary process. This justifies the definition of locally stationary t. If for small time windows we can approximate our process by a stationary process. This is only heuristical up to now. Yes. So let's come to some examples. And important examples are time-varying autoregressive moving average processes. You know, in the stationary case, such processes, there we have here constants only, here and here. And then then we know that our normal autoregressive moving average processes, solutions of this recursion equation. And these are stationary processes. But if we change the constant coefficients here to time-varying functions, then we get locally stationary processes. And we can show that solutions of this recursion equation fit into our definition. For example, on the left-hand side, you can see a stationary autoregressive process of order 1 with constant coefficient 0.5. And you see over the time there is no change in the behavior of the statistical behavior. But if we have a time-varying autoregressive process, where here is a function that changes over time, I chose this one, then you can see that the statistical properties, of course, change because the variance of the process changes over time. What is also possible is to model oscillation errors with such time-varying autoregressive processes, as you can see here. For this, we had to choose autoregressive process of order 2, and then we have to choose some functions to get as such in behavior. What is also possible is something like a time-varying arch process, but it's important that this does not fit in our definition because we know that such processes have a Volterra series as explicit representation. But I wanted to show this so that you can see what would be possible if we allow for nonlinear, locally stationary processes. So what we could see is that often for many interesting locally stationary processes, we can split the process in a model part and a part of an unknown parameter curve. For example, in the time-varying autoregressive process of order 1, we know this is the definition, and then the model part would be something like only the stationary recursion equation, and the unknown parameter curve would be theta 0. From now on, we assume that the model part is known. That would mean in this example that we know that we have an autoregressive process, but we assume that we do not know the parameter curve. And we want to estimate this function. Dahlhaus gave the following propose to tackle this problem. He defined for a locally stationary process this function A with the approximate coefficients and this so-called spectral density. And now he assumed that the function A could be represented as this function, which means that we can that A depends on the time only over an unknown parameter curve theta 0u. So now we split the model into two parts, an unknown parameter curve and this function. And our assumption that we know the model means that we know this function A theta. From now on, we know A theta. There are simple examples. If we take the autoregressive case, we know that the function A has this form. And so, A theta would have this form. And the same for the moving average case, with a little different form of A theta. Dahlhaus now proposed the following estimator. He proposed a kernel type estimator, which is given in this form. So you have a weighted likelihood, local likelihood with a kernel. And this likelihood at time step t is given by a conditional Gaussian likelihood of the process. And this is an approximation of a conditional Gaussian likelihood, which is called the Whittle likelihood, where this is a periodogram-like estimate. He showed that if the unknown parameter curve theta 0 is twice differentiable continuously, and theta fulfills some smoothness properties, then the maximum likelihood estimator from this function, from this likelihood, so it's the minimum likelihood estimator, it fulfills such an bias variance decomposition. In the special case that we have the autoregressive process of order 1, this is easy to see that we get this local likelihood function, so it's very, it's natural. And the estimator is then the quotient of the first and the 0th local covariance with such definitions. And one can see here that the difference from the estimator minus the true function takes this form. And now we come to the problem how to choose the bandwidth h. And because of this expansion here, one can see that it's not so easy as in the normal kernel regression case, because the variance will depend on the unknown parameter function, and we have a quotient and so on. It's not so easy, and so it seems not easy to work with oracle inequalities or something. And so I first decided to use a cross-validation method. And now is the goal under which conditions we can say something about the theoretical behavior of such a cross-validation bandwidth selector. Yes, it turns out that when one looks at the estimators, that we cannot use directly the estimator that was proposed by Dahlhaus and which I presented before, because the Whittle likelihood has the problem that it uses also values in the future to estimate the parameter value. And this is not good because this destroys the projection behavior of this likelihood. So our new propose is to use the following theorem. If we know that the spectral density, or this function a theta, is bounded uniformly from below, then we can, of course, define coefficients, Fourier coefficients of the inverse of this function. And it is known then that if we have this stationary process, we can invert this stationary process and can represent epsilon by a linear combination of the axis. And this can be interpreted as a prediction error, because here stands something like we want to describe xt by terms x with index greater than t. 8 greater than t. And if we now not use our stationary approximations, but our really observed locally stationary process, then we can see that such a finite sum can again be interpreted as a projection error plus other errors, namely an approximation error, which takes into account that we only sum until t, minus 1, and the approximation from the locally stationary to the stationary part. And then we have a bias term that comes because of the u. This motivates to define a new local likelihood. And for this, we use the likelihood at time step t of this form, which can be interpreted as a prediction error at time step t for predicting xt by the axis with lower indices. And then the kernel type local likelihood. And then we define our new estimator as a minimum likelihood estimate, maximum likelihood estimator. Only to see what we get in the special cases. In the special case of the autoregressive process, we again get the same as before. There changes nothing, but in the moving average case, there changes something, and we get this form. Now we define the cross-validation method, and it's very natural how it have to be defined. We use a leave one out likelihood, where we delete the Thief's summon, and then define a local leave one out estimate for theta. The cross-validation function is defined via plugging in the leave one out estimate in the likelihood function at time step t, and then h is of course the minimum of the cross-validation function. In practice, we cannot show that that this is continuous. So in practice, of course, it works because we have a discrete field over which we have to minimize. But exactly, we have to do here. Yeah, we have to talk a little bit more about this. Now we want to state our results for this cross-validation method. And for this, we define a distance measure between the true function and our estimator by a squared distance with a weight factor here, which is a spectral Fisher information. So we could interpret this distance as a Kullback-Leibler type distance measure because we write with this spectral Fisher information matrix. And of course, we know this Fisher information.
This matrix is used as a weighted matrix. Why? Yes.
Yes?
It's a weighted norm.
Yeah, it's this time.
Okay.
Yeah. It's a weighted norm. And this, again, is a scalar product, of course. Because we know A theta and F theta, we know this spectral Fisher information. And so we know how this looks like. Now we come to the assumptions we had to make. And this is a little bit, it's many assumptions, but they are not very hard to understand. The first two assumptions here, identifiability and this interior and compact assumptions, are usual assumptions that have to be made that the maximum likelihood estimator is well defined. Then we have to assume that A theta is 4 times differentiable because we have to do some Taylor expansions. And we have to assume further that the function A theta is Hölder continuous in lambda with some coefficient greater than 1. This is to bound some Fourier sequences that come up in our proof. And we have to assume that this spectral Fisher information is uniformly invertible, or the smallest eigenvalue is uniformly bounded from below. And this is needed because we want to write the maximum likelihood estimator in the usual form. And to guarantee that this is invertible, we need that the spectral Fisher information is invertible. Yes, these are the first assumptions. And the second assumptions are only well known. We have to assume a Lipschitz kernel with compact support. The right function, which was in this cross-validation and in the distance function, has to be bounded variation, and the support has to have a support which is not beginning by 0 and ending by 1. It has to be a little bit away from this bounds. We have to assume that all moments of the errors are finite, which is needed because we use something like exponential inequalities. And we have to assume that our bandwidths are bounded from below and from up by polynomial bounds. And the unknown parameter curve, this is the important assumption, has to have bounded variation and has to be Hölder continuous with a coefficient. Under these assumptions, we can show that the cross-validation procedure is asymptotically optimal in this sense that if we plug in the cross-validation bandwidth, we get asymptotical the minimal distance for this DA. Yeah, this is a result which stated in the kernel regression in the normal IID, also a model by Hadler and Marin, and we adopted the proof. The proof is the core of the proof is to show that the distance measure dA, which we defined before, but now with the leave one out estimate, is near the cross-validation function. And then we can write this cross-validation function minus this term like this. Now we have to do Taylor expansions. We can show that the second term is near this. And so we have to use now our assumptions to show that the other terms go to 0 in with a rate. Yes, that's enough for the proof. The second theorem is assertion directly for the cross-validation bandwidth. We show that the distance can be approximated by a normal bias variance decomposition distance function, which has this form, and this variance and this bias can be calculated explicitly. And then we can show that the cross-validation bandwidth is asymptotical the same as the minimizing bandwidth of this normal bias variance decomposition. Yes, so these are the theorems we could prove. Now come some simulations for this. We can see that for the time-varying autoregressive process, it works well even for small sample sizes where we only have 100 time, where we have only time series of length 100. Here we can see the true theta 0. The green line is the global, estimator where we inserted the global plug-in, where we inserted this mini bandwidth which minimizes the mean integrated squared error, and we inserted the functions, the known functions. So it's the best. It's the best bandwidth we could choose, and the red one is the curve which we got when we used the bandwidth with cross-validation. So this is for small sample sizes. As it increases, of course, we get better results. And here is a box plot, a histogram, where we repeated the procedure 500 times, and we plotted the cross-validation bandwidth that we got, and we see that it's something like Gaussian around the bandwidth which minimizes the mean squared error. We can also plot the distance, the Kullback-Leibler distance we defined before in the cross-validation case and in the plug-in case, so with the optimal bandwidth, and we see that we get near the same distances in practice, but of course the cross-validation has a little higher variance. Yes, the second case is the time-varying moving average process. Here you can see the formula, and again here the results are a little bit have a greater variance. So the estimates have a greater variance because the estimator we cannot calculate the estimator explicitly. We have to use approximation methods to find the estimators. And the maximum likelihood estimator seems not to be good for the moving average process. And so, of course, the bandwidth estimator cannot give good results too. When the estimator theta is not good, then you can not get a good bandwidth estimator at all. And so we can see that here, if we make the same as before, 500 repetitions of this procedure, we see that again we have something like a Gaussian structure around the optimal bandwidth, but the variance is much more higher. Yes, and the distances are nearly the same in this case. But this is also because the estimator is bad, and so it's not so important which bandwidth we plug in. Yes, come to the conclusion. So we proposed a kernel density estimator and an adaptive bandwidth selection procedure via cross-validation for unknown parameter curves in such locally stationary processes. We showed that under mild assumptions, we can show mild assumptions on the parameter curve. We had only to assume Hölder continuity. that the proposed estimators are asymptotically optimal. Simulations show good behavior in the case of autoregressive processes, but if we have more than one unknown parameter curve, or in other processes like the moving average process, we get much more higher variance, and the results are not so good. And important remark, the cross-validation bandwidth is of course dependent on the quality of the maximum likelihood estimator. Our estimate at all is dependent on the quality of the maximum likelihood estimator. Yes, outlook, we would like to generalize this procedure to nonlinear local stationary processes, and it would be nice to have methods for local bandwidth selection, for example, via plug-in methods, but this is very hard to prove because these Taylor expansions are not so nice. This is all.
Some questions?
The last plot you compared this was a plug-in, this estimated, that's the next one.
This is not bandwidth, this is the distance. And this shows that we get almost the same distances with the cross-validation bandwidth when we use the cross-validation bandwidth.
The plug-in is where you use the asymptotic formula.
Where we use this function dm star star, which I had this, and then used this. Yeah, and then here I plugged in the true function, so I used the best estimator I could get with this outcome, with this formula.
Because this is very, very similar to
Yes.
the estimating the bandwidth is the same as you
Yes, but I think this is because the estimator is so bad in the MA case. So we have a big variance independent of the bandwidth. So it does depend on the estimator in this case.
So maybe I missed something. So you are using Lua cross-validation.
Yes.
So what I want is prove that in this context you cannot use Lua now. Because by using you have to remove the correlation between the observation and the rest. But if you have dependent data, you don't remove if you just only one observation. Usually in series context, one looks at the best prediction.
Yes, and that is what we did.
But then it always you call it one out, but it is actually
Yeah, I called it.
one step ahead prediction.
Yes, here here is the likelihood, the local likelihood times the t. I said this can be interpreted as a prediction error.
Okay, so you have some up to t minus 1.
Right.
You look only one.
On the one side, yes.
So it's just terminology.
Yeah.
You are perfectly right. Just because
And the problem was that we could not use the Whittle estimate, as explained before, because then this would go over the t. And we could not interpret this as a projection.
Okay, thank you. We don't have